Okay, so with this video, we'll talk about the solution for the last assignment, and different from before, we have 3 questions rather than 2. But actually, let's begin. So if the switch has been closed for a long time, so before t equals 0, the switch is short circuit here, and so it is closed for a long time, which means that it is in the DC steady state before t equals 0, but it is open at t equals 0. Determine the characteristic equation of the circuit. Actually, it is a second order. This is a second order circuit, so the characteristic equation will be a second order polynomial. And B, determine Ix and Vr for t is larger than 0. So first of all, we like to determine the initial condition for this circuit. So actually we can draw it here. For t is smaller than 0, we can just make this short circuit, and just we can ignore this, ignore the switch, and pretend it is just a wire. So here we may call this one V. We may call this one V, and we may call this current I. So actually, for steady state, the current for this part will be 0, which means Ix will be 0, and thus this is 16 volts. So this one is also 16 volt, and as this the voltage for capacitor should always be continuous, so V0 plus will be 16 volt. And in this case, we can also calculate the current. For t is 0 minus, and for the current for an inductor will also be continuous. So we know that I0 plus will be this is 16 volt, and for steady state, the voltage drop for an inductor will be 0, which means that it will be this is 16, this is 0, so 16 minus 0 all over 8, which is 2a, So actually this is a second order circuit, so we will also like to find the first derivative for the initial condition. And in this case, actually we can draw the circuit for t is larger than 0. So as long as the switch is open, which means that we can just ignore this part, and the circuit will look like this: 12 ohms series with 1 over 36 farad, and this is 8 ohm. This is 1 Henry. This is VR. And this is Ix. We're supposed to find, and this is I just assume, and this is V. So the green variable continuous, so it is easier to write, or it is not so easy to make mistakes if you write a differential equation according to this variable. But if you write an equation in this variable, it may be a little bit tricky. You need to be more careful about the initial condition for this variable. It is okay, but easier to make mistakes. So, we'd like to find the first derivative for v and I. And actually, as this one is continuous, which means that we may also call this one VL. So actually, VL 0 plus will be L, which is 1, di dt at 0 plus. Which means that di 0 plus dt will be VL 0 plus over L, and which will be L is 1, and VL 0 plus, as we know that this one is 16 volt. This one is 16 volt. This is 16 volt. This is 16 volt. And this is 16 volts. And the current I will be continuous, which means that this node is 16 volt. This node is 16 volt, and this is 2. This is 2A at t equals 0 plus, which means that the voltage at this point will be 16 minus 2 times 12 plus 8. So it will be like this, and this is 20. So 2 times 20 is 40. 16 minus 40 is minus 24 A over S. So it's a little bit tricky. So you need to be careful about that. This node is not 16 volt at t equals 0 plus. This node is not continuous. This voltage is continuous, and this current is continuous. So after this switch is open, this voltage is jump to another voltage. Actually, we can slightly calculate it, just like this is 16 volt minus 2 times 24. So this is minus 8 volt, at t equals 0 plus. And also, we would like to find, actually we don't really need to, we can actually write an ODE according to I, so we don't really necessary to find dv0 plus dt, but actually you can also find it, but it's not really necessary. So far we know that this is the initial condition. This is another one, I0 plus and di0 plus dt. So we can try to write the ODE describing this circuit, and actually it won't be very difficult. So first of all, we'll know that according to this capacitor, C dV dt, C is 1 over 36 farad, and dV dt should be Ix, because this is positive, this is negative. So the current direction should be this way. But if we want to use I rather than Ix, it will be minus I rather than Ix. Or you can, or actually it is equals to ix. So this is the first equation, and then for the second one, we can write the KVL for this loop, KVL for this loop. So actually, this is VL. VL is actually L di dt. L is 1 Henry. Di dt. And then this one I multiplied by A, and then I multiplied by 20. So we can plus A plus 12 times I. So this is the voltage drop for these two resistors in clockwise direction. And this is V. So we can write equals V. So this is a KVL. This is the IV characteristic of a capacitor. So this is a capacitor. This is a KVL for the whole loop. Okay, so we have two equations with two unknown. One is V, one is I. So we can simply eliminate one of them, like this. We can take the derivative of this one. So we'll have second derivative of I plus A plus 12 is 20, and then we take the first derivative. So we have di dt, and then minus dv dt, should be dv dt. We need to take the first derivative equals to 0. So we just did it by just did this by take the derivative of the whole equation, and then we get this one. So for the next step, we can substitute this one into here. So, and actually, like this. So we can actually write it as dv dt equals minus 36i. So dv dt is minus 36i, so minus dv dt is 36i. So we can write it as second derivative of I plus 20 di dt, and then plus 36i equals 0. So for part A, the characteristic equation is s squared. So we replace the second derivative with s squared, and then we replace the first derivative by s, so plus 20s plus 36. The origin function is replaced by 1, so actually this is the answer for part A. And then we would like to solve this ODE. Actually, we would like to solve this characteristic equation. So we'll get S is minus 2, minus 18, minus 2, minus 18, minus 20. So this is 20. Multiply together 36. So we have these two roots, two distinct real roots. In this case, I complementary solution. Actually, there's only complementary solution because there's no external force. For t is larger than 0, the voltage source is turned off. So actually, we can write that I is a to exponential to minus 2t plus b times exponential to minus 18t. Well, so we take the first derivative, which will become minus 2a exponential to minus 2t minus 18b exponential to minus 18t. Well, and then we substitute t equals to 0 plus. So we will have I 0 plus is a plus b, which is a plus b is 2a. So we have 2, and then d I0 plus dt is actually minus 2a minus 18b. Minus 2a minus 18b equals this one. This one is minus 24. Minus 24. So we multiply this one by 2 and then add them together, so that we will have by 2 add them together. So minus 16. So we have minus 16b equals minus 20, which means that b is actually 5 over 4, which is 1.25. And then we substitute this one into here, so that we'll get a is 0.75. 0.75. So we get a and b. And which means that I is 0.75 exponential to minus 2t plus 1.25 exponential to minus 18t. So this is I, but actually we would like to find Ix and Vr. And hopefully it is not too difficult, because Ix is actually minus I, which is 0.75 exponential to minus 2t minus 1.25 exponential to minus 18t a. So this is one of the answer we would like to find. And then we also like to find Vr. Vr is very simple. This is a resistor, so it is nothing but 8I. So for the other one, we would like to find Vr, which is 8I. So it will be 6 exponential to minus 2t plus 10 exponential to minus 18t volt. Okay, so this is the second answer for part B. Okay, so let's see the other one. So this is still a RLC circuit, but the components value are in a phasor domain. So we will try to find the phasor VO. And for this one, there are two easy ways to find these find the answer. actually you can use the source transformation, definite, and then convert to Norton, and then parallel resistance, and then parallel impedance, and then convert back to definite, and then series, and then convert to Norton, and then parallel, and then finally you can find VO. Or you can assume VO prime to be 1 volt, and then you try to go back. It may be an easier way to find this type of ladder circuit. And then finally you can find out that the VO's the source will be in another voltage, and then you use the linear property to find what VO should be. And in this solution, I'll try to use the source transformation to find the answer. So for the first step, this is definite. And then I'll try to convert it into Norton. So it will be 20 over 4, which is 5A. 50 degree is actually 5, but but we only write this to emphasis. It is actually is a complex number or a phasor, or it is not a DC, not a DC voltage. But in this question, we just need to care about the frequency, because all the impedance of the inductor, capacitor have been calculated for you, and actually you know that this should be -1 over j omega z, and this should be j omega l. So there should be a frequency for this source, but we don't really care about it. As long as you need to convert it back to time domain, then you need to know the frequency. But in this case, we don't really need to. So this is VO. So now we will like to find, this is 4 parallel J2, which is 4 times J2 over 4 plus J2. And it will be 1/5 4 plus J8. Yeah. And then we convert these parts back to definite. This is Norton. This is Norton. And well, it will be something like so this is 5, so the VS will be 5 times 1/5 4 plus J8, which will be 4 plus J8. So this source will be 4 plus J8, and then this one is 1/5 4 plus J8, and then minus J3 2, and then J4, and then minus J2 VO. Okay, so next, this is minus J3, this is 1/5 multiply 4 plus J8. So next, so as we so let's continue. So actually these two is in series, and it would be 4/5 plus J8/5 minus J3, which will be 4/5 minus J7/5. So this is the series impedance. And then we also would like to find 4 plus J8 over this impedance, 4/5 minus J7/5. And then after some calculation, we'll know that it would be minus 40/13 plus J60/13, something like this. So in this case, we can actually convert this part into, so this is definite, and then we convert it to Norton. So it will be minus 40/13 plus J60/13, and this is a current source, and then parallel with 4/5 minus J7/5. This is a impedance. This is an impedance, and then this is 2 ohm. This is 2 ohm, and then this this is J4, and this is minus J2 VO, something like this. And then for this one, this is Norton. This is Norton, when then we like to convert it back to definite for the final time. And actually, before doing that, we need to find 4/5 minus J7/5 parallel with 2, and this will be 6/7 minus J4/7 minus J4/7. And also we would like to find minus 40/13 plus J60/13 multiplied by this 6/7 minus J4/7, and this is a pure imaginary number, J 40/7. So as we convert this Norton equivalent circuit back to definite, so it will be J 40/7, and then series with this one 6/7 minus J4/7, and then this is J4, this is minus J2, this is VO. So as simple as this one, we can write VO is actually J40/7 multiplied by this one. In the denominator, it is 6/7 minus J4/7 plus J4 minus J2. And then we hope to find the voltage, VO. So we need to multiply it by minus J2. And in this case, the answer will be 3.53 minus J 5.88 volt. Or if you would like to express it in polar form, you can write it as 6.86 minus 59.0 degree volt. So you can actually write it in the Cartesian form, or the rectangular form, or the polar form. So this is the answer for question 2. And for the third one, actually this is not the circuit related question. This is actually about the Maxwell equation, the Gauss Law. And well, so let's see. So for an electric field in the sphere coordinate, like this, ER is this one. For R is larger than R0, it will be capital phi 0 over R squared, and within R equals to R0, the electric field is 0. So phi 0 is nm squared over Coulomb, so, and R is in meter. So the square surface vector A is defined as shown here, which is a square. Each side is in length d, and actually it is in the xy plane where z is equal to d. So in this case, A is in positive direction of z-axis, which is pointing upward, because for a plane, the direction of this area vector can be pointing upward or downward, but in this case we assume it is pointing upward, and d is larger than r0, and so we would like to find the total thrust for this integral, and the hint is using Gauss Law. So in this question, we would like to define a Gaussian surface S, which is a sphere, with radius r, where r0 is smaller than r, smaller than d. Which means that actually the surface is inside the space where E is larger than 0, and actually this surface is centered at the origin, which means 0, 0, 0. So in this case, we can draw a figure like this. So actually, S is a sphere like this. And actually, there will be electric field going through this Gaussian surface. So we can find that E dot dA, according to Gauss Law, which will be equals to Q enclosed over epsilon naught. This is to use Gauss Law. And we know that across this surface, the E dot dA is actually a constant, which means it will be nothing but 4 pi r squared is actually this is actually the area times the constant E. The constant E at R is nothing but phi 0 over R squared. And actually this one is the E R. This is actually E R, because we assume the radius of the sphere is R. So on the right hand side, it is Q enclosed of Q enclosed over epsilon 0. And then we can write it as Q enclosed equals, this R squared can be cancelled, so we have 4 pi epsilon 0 phi 0. So this is very important. And actually you can use the shell theorem to find this variable. Actually, or you can use shell theorem to get this step. Okay, so this is the first argument we would like to have. Just want to highlight it, and then we'll use it later. So next, we define another Gaussian surface. So we define another Gaussian surface. We may call it B because actually this is not S. This is not A. This should be S. This should be S. Gaussian surface B, which is a cube. Because actually in this question we're supposed to find the electric flux through a square. So we would like to construct a Gaussian surface, which is a closed surface that contains this part. So we would like to define a Gaussian surface, which is a cube, and with side lengths to be 2 times d, and then centered at the origin. Also centered at the origin. The size are parallel to x, y, z axis. So if we would like to draw this out, it would be something like a cube so every side is 2D, and then the center at the origin, and then 2D, 2D, 2D. Something like this. And actually we can also use the Gauss law. We would know that this will be something like Q enclosed because we know that for the previous case, R can be larger than R0, smaller than D, which means that this Q enclosed is actually enclosed by this sphere, and this sphere is totally inside this Gaussian surface. So in this case, and there will be no charge outside. There will be no charge outside. So in this case, we will find that this will be 4 pi epsilon 0 phi 0 over epsilon 0. So this will be nothing but 4 pi phi 0. 4 pi phi 0. And according to symmetric, actually, what we need to find is actually this part. This part is A. This is what we need to find. And the whole one is A. So there will be 6 faces for a cube, and this is actually 1/4 of a face. And we can see that this, for this electric first, for this electric first, for this electric first, for this electric first, they should all be the same. Which means that we can find that actually this is not a closed surface. This is not a closed. So this is the pure double integral. So this is what we need to find, which will be 1/24 B E dot dA. So due to symmetric. So this is the second one we would like to find. So we know that this one is 4 pi phi 0, and then we can substitute it here. So it turns out to be 1/24 times 4 pi phi 0. And then 4 and 24 can be partly cancelled, and it will become pi over 6 phi 0. And this is the answer. Okay, so this is all about the solution for the final assignment. And if you have further questions, please let me